Hello all, let's start with the kinetic energy of an ideal gas. So, you must know that molecules of ideal gas possess only translation motion. So, now the question is what translation motion is. So, translation motion depicts the motion when an object is moving in a straight line. So, whenever we take into account an ideal gas, so we have to consider that it is in translation motion. There is no other motion dependent. So now we need to find at three different quantity of gases. One is kinetic energy of gas molecule. So we would be only considering the single molecule. Suppose it has a mass m, small m. Now as you know the E molecule is given by half m Vrms square. Now from this equation we can easily find out Vrms based on small m. So we need to find Vrms square, that means under root will get cancelled out. So half m 3kt over m. Now m and m gets cancelled out. So we are left with 3 over 2 kt. So this is the answer when we have a gas, we are talking about a gas molecule. Next is kinetic energy of 1 mole milligram gas, E mole. So in this case we would be talking about m gram, big M. So MVRM is square. Now we need to find VRMS on the basis of bigger molar mass. So it will be M 3RT over M. Now M and M gets cancelled out. We are left with 3 over 2 RT. This is the answer for kinetic energy of 1 mole gas. Now we need to find kinetic energy of 1 gram of gas. So when we talk about 1 gram gas, it is given by 3 by 2 Rm over T. Now as you know, R can be written as 3 over 2 Kna over Mna, and Na gets cancelled out and we have T here. So it will be 3 over 2 Kmt, or you can write it as 3 over 2 Rt. So these are three different formulas for kinetic energy of a gas molecule, kinetic energy of 1 mole and kinetic energy of 1 gram mass respectively. So let's move on to the next part, which is some problems based on kinetic energy. Let's start with it. So the first one says the kinetic energy of 1 gram mole of a gas at normal temperature and pressure is. Here we are given with R value. So we need to find kinetic energy of 1 gram mole, and 1 gram mole is equivalent to 3 by 2 RT. The last formulas we did are very important, so must consider them. So E is equal to, in this case, 3 over 2. R in this case is 8.31 into, it says normal temperature, that means 273. So when you solve this, you will get your answer as 3.4 into 10 raised to power 3 joule. So the right option out of this is D part. Moving on to the next. The next says the average translation kinetic energy of oxygen molecules at a particular temperature is 0.048 electrovolt. The translational kinetic energy of N2 molecules in EV at the same temperature is. So as you know that the average translational kinetic energy isn't dependent upon the molar mass of the gas, so therefore different gases will possess same average translation kinetic energy at same temperature. So if O2 has 0.048, then nitrogen 2 have 0.048. So the right option is C part, 0.048 electrovolt. Now the next one, it says average translation energy and the RMS speed of molecules in a sample of oxygen gas at 300 Kelvin are 6.21 and into 10 raised to power minus 21 joule and 484 meter per second respectively. The corresponding values at 600 Kelvin are nearly assuming ideal gas behavior. So we need to find the corresponding values at 600 Kelvin. These are the values at 300 Kelvin. This is the translational energy and this is the RMS speed. We need to find at 600 Kelvin. So this is for oxygen. Again, this is for we need to find for oxygen. So as you know that E is directly proportional to T, and you know that VRMS is under root of T. So that is, you can see that if temperature becomes twice, then energy will become 2 times. So it will be twice of 6.21 into 10 raised to power minus 21 because E is directly proportional to T. So twice of 6.21 will be 12.42 into 10 raised to power minus 21 joule. Now VRMS is directly proportional to under root of T. So here we need to take under root 2 times 484, the RMS speed of oxygen molecule at 300 Kelvin. So the value will be, when you solve this, it will be approximately equal to 684 meter per second. So the right answer in this case is D. Let's move on to the next one. So in this case, we are given with a box containing n molecules of a perfect gas at temperature T1 and pressure P1. The number of molecules in the box is doubled, keeping the total kinetic energy of the gas same as before. If the new pressure is P2 and temperature T2, then we need to find the number of molecules in the box is doubled actually. Let's find out what will be the answer. Now, if we have n molecules, we have 3 over 2 n kT. Now, initially we have E1, suppose, so it will be N1, K1, T1. K is constant, so I will be keeping it as K. Now, final one will let it be E2, so 3 over 2 N2 K T2. Now, according to this problem, it says that E1 is equal to E2, but N2 is equal to twice of 2N1, and it says they are equal. So 3 over 2 N1 KT1 equals 3 over 2. N2 can be replaced with 2N1. So twice of N1. K is same, so I will cancel it out. T2 is same. So 3 by 2 and 3 by 2 gets cancelled out. From this equation, we are left with only N1 T1 equals N1 T1 dot twice of N1 and N1 again gets cancelled out. So T1 equals twice of T2. So this is the condition that T1 is equal to twice of T2. Now, as it says, the kinetic energy is constant. So from that, I will get N1 T1 equals N2 T2. This is another equation. So that means Nt is constant from this. If Nt is constant, that means it is an ideal gas equation of n molecule, and it suggests that P1 is equal to P2. That means the answer to this will be T1 equals twice of T2 and P2 equals P1 from ideal gas equation. So the right option is B part. Moving on to the next. Now we have three closed vessels, A, B and C are at same temperature T, contain gases which obey Maxwellian distribution of velocities. Vessel A contains only O2, B only N2, C is mixture of O2 and N2. So we have three boxes. Let's make some visuals. A has O2, B has N2 and C has O2 plus N2. If the average speed of the molecule in vessel A is V1, that of N2 is V2, and the average speed of O2 molecules in vessel C is. So we need to find the average speed of gas molecule in C part. So actually if I talk about this, the average speed of the molecule depends on temperature and molecular mass. So there is no change in the temperature and the molecular mass as suggested by this. So VRMS will be same as of the first one for oxygen molecule. That means the C vessel and the average speed of oxygen molecules in this will be V1 only. And if they say that you need to find average speed of the oxygen molecule and nitrogen molecule, then it will be V1 plus V2 if there is such condition. Otherwise, the answer in this case is V1 only. So that's all for today's lecture. I will continue tomorrow with the next session. Thank you for watching this.